the volume of a box with a square base is fixed at 50 cubic centimeters. So we have a box shape. Is it a cube? Not necessarily. There's a box shape. But it does have a square base. I didn't really draw it to look like a square base. This is supposed to be a square base. You need to imagine this picture with perspective. Evidently, looking at the formula for the volume as x squared times h, evidently x is the length of each side of the base, and h is the height. So we see the volume is the area of the base, which is a square, x squared, times the height. We're saying that's fixed, that's given to be 50 cubic centimeters. That's the constraint. The constraint is that x squared h has to equal 50. In other words, x and h are not free to vary independently of each other. If the volume of the box is going to stay constant at 50 cubic centimeters, if you increase x, you got to decrease h. They're related variables. You could say one is a function of the other, and in fact, that's what I do next, is I tell you, you can solve this for h as a function of x. I told you that in this problem on exam 2. I guess one other change I could make is not tell you solve for h in terms of x. You should know that. Okay, we've done problems like that before. You're doing it on this old exam. I told you what to do, but you should be able to solve for h as a function of x and know to do that to help you ultimately now minimize the surface area. The surface area is going to ultimately be a function of x. I'll call it f of x. I didn't do that in the problem, but I could have. Initially, it seems to depend on two independent variables, x and h, as if it's a multivariable calculus function, but because of the constraint, we can reduce the number of variables. The h can get replaced by 50 over x squared. X does need to be positive. You could say the domain of this is all positive values of x. This is the function that we want to minimize. We want to find the value of x that makes this function as small as possible. So you want to use calculus. Some of you didn't bother using calculus. The point is to use calculus. Take the derivative. Find the derivative of s with respect to x, or if you've got function notation, you could write that as f prime of x. Some of you didn't bother simplifying this. It is a good idea to simplify this. You don't need to use the product rule. You can write that as, well, one factor of x cancels. You can write it as 200 over x. And you don't even need to use the quotient rule, because 200 over x is the same as 200 times x to the negative 1 power. You can just get away with the power rule. Make things simpler on yourself, okay? In this case, simplify before you differentiate. I know with the gateway, we talked about taking derivatives and not simplifying, but when you're doing regular exam problems, it is often good to simplify functions or their derivatives. So now we take the derivative. Derivative of x squared is 2x. Derivative of this, bring down the negative 1, you get minus 200. Negative 1 minus 1 is negative 2. Set this equal to 0 and solve for x. Doesn't look so easy, but it is doable. You could add 200x to the negative 2 to both sides and write it as a fraction on the right. And then I hope that's enough of a hint that you should probably try isolating x by first multiplying both sides by x squared and dividing both sides by 2. So x cubed is 100. So it seems like our critical point here for x is the cube root of 100. Also could be written as 100 to the 1/3 power if you like. Okay? And that's fine. Do you need to simplify it? Not really. You can just leave it as cube root of 100, though it's nice to see approximately what it equals. 100 to the 1/3 power It's about 4.64 centimeters. The question is asking for the dimensions x and h that minimize the surface area. That's one of the dimensions. We also need h. You do not need to prove that s is minimized here to finish the problem. I'm not ruling out on the final if I put something on here saying you should prove s is minimized. I'm not ruling that out. Write that down. It's probably easiest to verify that the second derivative is always positive. And it is here. The graph is concave up. Technically speaking, when you evaluate the second derivative at the critical point and see that it's positive, so the graph is concave up, that only verifies that it's a local min. However, it will be a global min here because the second derivative is always positive when x is positive. If I take the second derivative with respect to x using either notation, I'm using both. You don't have to use both. I differentiate this function here as is. I get 2. Bring down that -2. I get a plus 400 x to the -3 power. And it doesn't matter that that exponent is negative. When x is positive, this is a positive quantity. This is positive for all values of x that are positive. We don't care about negative values of x because that's not relevant for lengths. So that means the graph of f is concave up when x is positive. So it's got to be not just a local min, it's even got to be a global min for the application at least. I didn't ask you to verify that. In fact, I explicitly said you don't have to, but I'm not ruling out on the final asking you to verify that if I put something like this on the final. As far as the value of h goes, use the constraint. H equals 50 over x squared. H equals 50 over x squared. You could write that as 50 over 100 to the 1/3 squared, which is 100 to the 2/3. That's one way to write the answer. There's various other ways you could write it, the answer. One thing kind of surprising here, actually one thing interesting is if you do multiply the top and the bottom of this by 100 to the 1/3 power, which doesn't change its value because you're really multiplying by 1, you get 50 times the cube root of 100, and 100 to the 2/3 times 100 to the 1/3, if you add the exponent, is 100 to the first power, 100. And then the 50 cancels with the 100 to give you 1/2 cube root of 100. The height is half the base. That's interesting. About 2.32 centimeters. Maybe that's something that generalizes to any box with an open top. Maybe. I think it does. Any rectangular box with an open top is going to have a minimum surface area when the dimensions are such that x, the base length, is twice as big as the height. In other words, my drawing is off. It should be a shorter box. It should be a box more like this. When the top is open, there's no top up here. It's an open box. The surface area is minimized with this kind of shape for a given volume. Could be a practical thing to know if you are a company that makes boxes and would like to have them a certain volume, but keep your cost for your cardboard minimized. Cost for cardboard should be proportional to the amount of cardboard, right? Sounds like a practical thing if you don't really care about the shape of the box exactly. Let's look at this implicit differentiation problem next. Initially phrased in terms of a multivariable calculus function, because I taught you a little bit of multivariable calculus as well. We've got this function f of xy of two variables, x squared minus y cubed plus x squared times y squared. When you think about this function in multivariable calculus, you are thinking of x and y varying independently of each other. Y not being a function of x, getting a graph that's a surface in three-dimensional space. But when you think about what are called level curves of this, where you slice that surface with horizontal planes and get curves called level curves, there, along some curve in the xy plane, that curve does define y as a function of x. And it's essential with implicit differentiation that you make that assumption. If you don't make that assumption and understand what you're doing when you make that assumption, you're completely missing the point of implicit differentiation, and you get the wrong answer as well. But anyway, part A is supposed to be easy. Just find f of 2, 1, plug in x equals 2 and y equals 1 and see what you get. We get 4 minus 1 plus 4. We get ultimately 7. The C in this problem is 7. Yeah, part B says call your answer C. Then the resulting equation for part B, f of xy equals 7, equivalent to saying x squared minus y cubed plus x squared y squared equals 7, is an equation only involving x and y, no z. It does define a curve in the xy plane. Is that always the case? Does it always define a curve, no matter what f of xy is or what c is? That actually doesn't always define a curve. It could define the empty set. There might be no solutions. Sometimes it might just be single points that are solutions. Generally speaking, it does define some smooth curve. This defines some smooth curve. Can I draw it? I'm not good enough to be able to draw this without technology, so you shouldn't be able to expect yourself to either. However, I can use implicit differentiation to help me find the slope of this curve near the point in question, near the point with coordinates 2, 1. I know that point is on the curve because when I plug that point into f, I got 7. And that's what this curve is, where f of xy equals 7. So that is a single point that I know on the curve. My goal in using implicit differentiation and then in linear approximation is to try to find approximate nearby points on the curve. That might be a practical thing to do if you want to program your technology to draw the curve, if you don't have some fancy program that does it for you already. Actually, you've got to use even fancier techniques, but it's a hint about something you might try. Okay, it's a first step. So we assume, I can't emphasize this enough, we assume y is a function of x when we look at this equation. Technically, near the given point, x is 2, y is 1. Is that true? Not necessarily. It's possible the graph might just be a dot or the empty set for all you know. It's also possible the tangent line might be vertical at the point. It's not likely, but it's possible. A teacher could make an example where that happens. And then if the tangent line is vertical, the graph might look like this near the point. It would fail the vertical line test, and y would not be a function of x near the point. But that doesn't typically happen. I won't make it happen even on the final exam, if I put this on the final exam. But you differentiate everything with respect to x under your assumption. X squared differentiate with respect to x is 2x. Y cubed, when you differentiate with respect to x, is not 0. It's not like a partial derivative. I'm assuming y is a function of x. Y cubed is like f of x cubed. Oh, well, I shouldn't call it f. G of x cubed for some unknown function g. I have to use the chain rule because of that assumption. I would get 3g of x squared, which I'll write as 3y squared, times the derivative of g, times g prime of x, which I'll write with Leibniz notation as dy dx. Probably the most common mistake for people who started this correctly was in the next step of not realizing they needed to use the product rule here. This is x squared times y squared. In other words, x squared times, say, g of x squared. I have to use the product rule as well. Lefty right plus righty left. Left, x squared. D right, the derivative of y squared with respect to x is 2y dy dx by the chain rule again. That's lefty right plus right, y squared. D left, 2x. 7 is an honest to goodness constant. Differentiate it to 0. Okay, that differentiates to 0. Don't forget that. What results now is an algebra equation that you can solve for dy dx. If you got this far, got that far so far without making a mistake, then you were pretty close to finishing. Factor out dy dx out of the two terms that involve dy dx. What are you left with? 2x squared y minus 3y squared. Bring the other terms to the other side, negative 2x minus 2xy squared. Then divide both sides by what dy dx is being multiplied by. And I think I will also switch around the order of this, make it a 3y squared minus 2x squared y, so that I can put plus signs in front of these things. Not that you have to do that. There is the general derivative for y as a function of x, as long as we're not dividing by 0. And then you'd want to evaluate this at the point 2, 1 and see what you get. I think I don't want to finish this problem for the sake of time. You get a number. Then that's going to be the slope of the tangent line there. Plug into your slope point form for the equation of a line to find the equation of the tangent line. Solve for y. And then plug in the last part, x equals 2.2 into that. By the way, x sub 0 will be 2, so it's easiest not to simplify this. Because when you plug in x equals 2.2 here and x 0 equals 2 here, you get 2.2 minus 2, something very simple to calculate, 0.2 times the slope, and then plus y sub 0, which is 1. This is a 2, this is a 1. M is whatever you get here. This is the m. Then you just replace x with 2.2. Okay? To find the approximate value of y when x is 2.2. Problem 16 gave people trouble as well. We're approximating cube root of 10 in 2 ways. I did give you help with this, so something you should be able to do. You just need to use the right formulas, essentially. So in part A, f of x is the cube root of x. Because we're trying to approximate the cube root of 10, we're trying to approximate f of 10 for part A. Just take it step by step. Part 1 of part A says, show work that confirms the local linearization is this. 2 plus 1/12 times in parentheses x minus 8. You just have to use the formula for the local linearization. Here it is. And then you plug in a equals 8. So you need f of x, which we already have. You also need its derivative, 1/3 x to the negative 2/3, which is the same as 1/3 x to the positive 2/3. A is 8. So we get f of 8 plus f prime of 8 times x minus 8. F of 8 is the cube root of 8. That's 2. F prime of 8. Plug in 8 for x there. 8 to the 1/3 is 2. Then when you square that, you get 4. 3 times 4 is 12. You do get 1/12 for the derivative. There you go. That's all you have to do. Part 2 says use L of 10 to approximate the cube root of 10. The cube root of 10, because of how f is defined, is f of 10. But the idea of linear approximation is this is approximately L of 10. Now just plug 10 into here. 2 plus 1/12 times 10 minus 8. 10 minus 8 is 2. 1/12 times 2 is 1/6. You get 2 1/6 or 13/6, which is 2.16 repeating. That's all you had to do. For the error in the approximation, E of 10, it's the actual value minus the approximate value. So that's the actual cube root of 10 minus 2.16 repeating. This could be positive, it could be negative. Cube root of 10 is about 2.154. Subtract 2.1666666. You get a negative number. It's a negative error. You should keep track of that negative sign. If you made it positive, you got a little half a point or point taken off. I forgot how much I took off. Some of you computed relative error. You also divided by the initial amount. That's not what was being asked for here. That's the error. The fact that it's negative says the approximation is too big. I didn't ask why it was too big, but if I did ask why it was too big, you should be able to explain. I'm telling you right now. Why is it too big? I might put this on the final. Draw a graph to see why it's too big. There's the cube root function. It technically goes over here as well. A is 8. Its value at 8 is 2, because the cube root of 8 is 2. In using the linear approximation, we're using the tangent line at this point. Because the graph is concave down, the tangent line is above the graph. So L of 10 is going to be bigger than F of 10, and this difference is going to be negative. The error is negative when your approximation is too big. It sounds a little strange, but that's the way it goes. Part B was about using Newton's method. There it is. We're still trying to approximate the cube root of 10, but now we're doing it with a different function. Not the cube root function, but x cubed minus 10. We're looking for a root of that equation. The graph of x cubed minus 10 looks, well, something like this overall. We're after this value, that's going to be cube root of 10 using Newton's method. I told you the Newton's method formula. If I put this on the final, I might not tell you. Should put it on your note card. Okay. It's a recursive formula. Xn equals xn minus 1 minus f of xn minus 1 divided by f prime of xn minus 1. We could use n equals 1 here if we like. And then we have x sub 0 minus f of x0 over f prime of x0. So that if you want to simplify it without plugging numbers in, you can. You don't have to. You would get this. Now just plug the number in. I told you to plug in 2.5. You just do 2.5 minus 2.5 cubed minus 10 divided by 3 times 2.5 squared. You could do it with the previous answer if you like. Plug in 2.5. Go previous answer minus, use parentheses, previous answer cubed minus 10, all divided by 3 times the previous answer squared. I'm being extra picky about making sure I use parentheses here. 2.2 is what you should have gotten. Is that equal to the cube root of 10? No. Not too far off. If I had done Newton's method again, which I'm not ruling out having you do with your calculator on the exam, previous answer minus, okay, previous answer cubed minus 10, all divided by 3 times previous answer squared. Enter it again. Enter it a couple times maybe. It converges pretty quickly. All of a sudden, we're at a point where the numbers don't change very much anymore. In fact, you can't tell a difference there between what, I don't know if those are like x4 and x5. And that essentially is cube root of 10. Good enough approximation that the calculator, when I cube it, is rounding to 10. In reality, the cube root of 10 is irrational. The decimal expansion goes on forever and ever without a repeating pattern. I will tell you that I will not put constant function theorem proof on the final, but I think it's worth talking about this one briefly. In this problem, we're assuming f prime always equals g, g prime always equals f. What functions are these? I'll tell you in a minute. Prove that f of x quantity squared minus g of x quantity squared always equals c. And I told you how to get started. Define a function h by that formula. We want to apply the constant function theorem. How do you apply a theorem? You need to verify the hypotheses are satisfied. And then you know the conclusion is satisfied. And you hope that's good enough. What are the hypotheses? You need to verify this function h that we're going to evidently apply it to is continuous and differentiable and always has the derivative equal to 0. then you'll know it's constant, and that will mean you're done. How do I know it's continuous and differentiable? Because f and g are. Done. In fact, if you just said, note that h is continuous and differentiable everywhere, I didn't even require you to say because f and g are. But that is the reason. H is a simple algebraic composition or combination of f and g. If f and g are continuous and differentiable everywhere, so will h be. We knew that from chapter 1 and the beginning of chapter 2. So h is continuous and differentiable everywhere. If you didn't mention that, at least, I took off a point for all x. The chain rule needs to be applied to differentiate h. If you didn't mention the chain rule, I took off a point. Even if you got the derivative right, it's 2f of x times f prime of x minus 2g of x times g prime of x. I put extra parentheses there I don't really need, but there we go. Whenever you try to prove something, you have to use your assumptions. I haven't used my assumptions that f prime always equals g and g prime always equals f yet. Use that. This simplifies to 2f of x g of x minus 2g of x f of x. Hey, I'm subtracting two things that are the same. That's always 0 for all x. I verified the derivative of this function is always 0. Therefore, I can now apply the constant function theorem to say h of x equals some constant c for all x. And that's what I really wanted to do because of how h is defined. Done. Okay? Verify the hypotheses are satisfied. Then you know the conclusion is satisfied, and the conclusion is what you need. The hardest part of the problem actually is the start, realizing that's what you should do. Define h to be f of x squared minus g of x squared. I helped you with the very hardest part of the problem. Okay, I'm not saying people found it this easy. Many of you had difficulty with this. Okay. But we did do an example very similar to this. And I won't put this on the final, and that's a guarantee. I was uncertain, and somebody asked me, will I put this on this exam? And I said, well, maybe not, but then I changed my mind. No, actually, that's referring to Newton's method with that. But this was definitely something that I said could be on this exam, but I'm not going to put it in the final exam. What functions are f and g? They're not sine and cosine, but they are seemingly related functions called sinh and cosh. What? Sinh, cosh? Those are functions you maybe never heard of. Actually, they're in the book. They're in section 3.7 or 8. We skipped that section. This is called hyperbolic sine and hyperbolic cosine. What are these? They're actually not sine or cosine. They're actually exponential functions. 1/2 e to the x minus 1/2 e to the negative x for hyperbolic sine, and 1/2 e to the x plus 1/2 e to the negative x for hyperbolic cosine. They're called linear combinations of those two exponential functions, an exponential growth and an exponential decay. And they do have the property, you can check it, the derivative of hyperbolic sine, check it with the chain rule, is hyperbolic cosine. And the derivative of hyperbolic cosine is hyperbolic sine. So they kind of act like sine and cosine. That's part of the reason we use similar notation for them. The connection between sine and cosine is even deeper if you use imaginary numbers. I won't go into depth any more than that. But they're actually very, very much related to sine and cosine when you use imaginary numbers, because sine and cosine are related to the exponential function when the exponent of e involves the imaginary unit I. This is true. This is called Euler's identity. And if you use it when x equals pi, you get that e to the I pi is cosine pi plus I sine pi. Cosine of pi is -1, sine of pi is 0. So e to the I pi is -1, which means e to the I pi plus 1 equals 0. And that, my friends, is the most beautiful equation in the universe right there. Aliens would agree. If you're abducted by aliens and they say, we'll let you go if you tell us the most beautiful equation in the universe, you've got the answer right there. You're home free. Why is it the most beautiful equation? Isn't it obvious? It's got the 5 most important numbers in it: 0, 1, e, pi, and I. Those are the 5 most important numbers. If you're a physicist, c is not a number. Speed of light. H bar, if you know a little quantum mechanics, those are physical constants that are not numbers. Did you know that physical constants are not numbers? Did you know that? They're not numbers. They're physical constants. Wait, what's the difference? They have numerical values, but those numerical values depend on the units you use. So they're not numbers. They have numerical values based on units, but they themselves are not numbers. Physical constants are not numbers. Don't let anybody ever tell you otherwise. Okay? Anyway, that's an aside for fun. We go into more depth about why that works in Calc 2.